Okay, we're going to start talking about circuits. Um, at the core of pretty much every electrical circuit is the movement of charge, okay? You have two types of charge in the universe. You have positive charges and you have negative charges, right? And we usually just indicate them with a plus or a minus. Now, we don't really need to care too much about the nature of these positive and negative. I mean, the charge you most often encounter in electronics is actually the electron, which is a negative charge, okay? But you don't have to have just electrons, right? You can have anions, right? Like maybe the chloride ion, right? Both of these are charged particles and they will move based off of an electric field. You also have, a lot in semiconductors, positive charges, okay? And these are actually, so the main negative charge in electronics is going to be the electron, right? And the main positive charge in electronics, outside of, chemistry and maybe some battery stuff, is actually something known as the hole, okay? And the hole is actually, I mean, we're not going to go into quantum and stuff here, but really it's neat to think about that the hole actually is the absence of an electron. So conduction and the flow and current is the movement of charge, just so we know, get that definition out of the way. So whenever charge moves, this is current actually. And current is defined as the movement of positive charge. So if you have one positive charge moving to the right, we would actually say we have, an I going in this direction. If we have a negative charge going in the opposite direction, it's actually the same thing, so these are equal to one another. And so that's the tricky thing, because a lot of times in electronics, especially circuits like we deal with, even though we say I is flowing to the right, actually in real life, if we were to zoom in with our scanning electron microscope or something, we'd actually see electrons are moving to the left. But from our perspective, actually, we don't need to worry too much about the fact that it's actually, negative charges moving. We can actually just think of it as, okay, there's positive charges moving around and this is good. So we have this current, okay, and this is, again, the movement of positive charge. And let's just think about life as if there's positive charges out there. Forget the fact that there's electrons. I know there are. I know that's actually what's happening down below in our electrons with resistors and stuff, but we'll just assume that it is positive charges. So in electronics, I think a lot of times people have seen circuits sort of that might look something like this. And this is usually like a battery or something, which people have seen. And then maybe there'll be, I don't know, a classic one from a physics textbook is like a light bulb, even though we're basically not using these light bulbs anymore, but whatever. So I don't know, maybe, and it glows or something maybe. And if we were to think about it from a circuit perspective, what's happening actually is this battery serves as a potential energy booster, and then the potential energy is lost through the light bulb, okay? And it's given out in the form of light and heat, probably too. All right, we're going to think about circuits a little bit differently, and the main reason is because we don't really use batteries in this class, first of all, and even just as an EE, actually a battery means something very specific, and we're not doing batteries. So we're going to actually forget about it. So let's draw a circuit. We're going to actually draw a voltage source right here, and this is the symbol for a voltage source, and we're going to do a 3.3 volt source because that's what we've been dealing with in class. That's what our Raspberry Pi puts out. And then this is going to go up with a wire, over with a wire, down through what we call a resistor, the zigzag, and then back down to the bottom, okay? And what happens in this circuit is you have charges, all right? And they're boosted in energy. Their potential energy is given to them as they move up through this voltage source. So up here, there's more energy in the positive charges. They're more excited than down here. What happens is then they can flow along here. There's actually no benefit or loss for them to move all over the place. Like a wire is actually an energy neutral spot relative to itself, right? So positive charges over here, the same as positive charges over here in terms of energy. When they hit that resistor, though, they actually will, because they're excited and they see that on the other side of this resistor is a lower energy spot, as they move through it, so you have these positive charges, as they move through it, they will lose energy and give it off, okay? And then back down here, they're at this low state. Now, this is really analogous to if we have the Earth, okay, and this is a RTH. Okay, and this is our planet, right? And then you have gravity, of course, right, which we know. All right, and you have some, I don't know, basketballs or sports balls or some sort of thing. I don't know. And there's a person, and they're just standing around. And then they're actually picking up the balls and putting them up on some sort of ledge up here. Okay, so then all of a sudden, there's balls maybe, 10 feet up or something. There's some height. Okay. So in this analogy, actually, the human is very similar to the voltage source. So we have these, basketballs or something, and it's lifting it up and putting them at a higher potential energy, right? And these balls can actually then roll off, right, and release that potential energy. And they can release that potential energy in the form of heat, sound. If they explode or something, it could even be like, I don't know, pressure thing. I mean, just differing forms of energy. But the energy that this person put into moving the balls up is then released when they fall down. Okay, energy goes out, and then those balls, once they are back down here, are at the same energy state as the balls right here. And this is exactly what's happening in an electronic circuit. The charges are down here. They're given energy, and then they release that energy through the resistor. Okay. And this resistor is a generic sort of device. Even though there are actually specific things known as resistors, this is a good model for pretty much any sort of device which takes an electrical potential energy, converts it into some sort of external thing, right? So a speaker could be an example of a resistor, a light bulb, an LED, just various things like that. So as these electrons fall, they give off, energy is given off, and that can be in the form of light or heat or something else. And this movement of these positive charges, as they're moving around the circuit like this, we're going to call that current, okay? Alright, so they're just moving and moving and moving around, and it's a cyclical process, basically. So they're boosted, then they fall. They're boosted, then they fall. This is known as the current through the circuit. This is our resistance right here. Let's call this, I don't know, let's make this blue resistor, and then let's make, I don't know. Let's make the voltage purple. Okay, and this is known as Ohm's law. So you have V equals, let's do red, I, R. Okay, voltage equals current times resistance. So what this is saying is the more energy. So what is resistance in this analogy? Resistance would be like wind resistance. Oh, no. So we're adding energy to the system, and it's important to remember, and this is like a good moment to think about what is a volt. So when someone says volt, what is it? A volt is actually a joule, if I could spell, a joule per coulomb. So for a given resistance, let's say, if we were to increase V, I would increase as well. Okay, for a given V, if we were to lower R, I would go up. So there's different trends here, right? So if we have just a circuit, let's say, with 5 volts, and we have a 1 ohm resistor, right? We can actually figure out that the current flowing through the circuit would end up being I equals 5 volts over 1 ohm, which equals 5 amps. All right. If we were to go and change this to 10 ohms, we'd actually see that I would drop to 0.5 amps. Okay, if we were to keep it at 10 ohms and make this 25 volts, we'd see that then I goes to what? 25 divided by 10 would be 2.5 amps. Now we have this circuit we drew, voltage source, resistor, and a lot of circuits that we build, they're not going to have a ton of just arbitrary resistors, but they're going to have lots of like things in them, right? Maybe there's some weird other component right here, then something else which goes through here, which then has a resistor on it, and then something else, and then just all these different things, resistor, capacitor, resistor, what, just random things. This gets really annoying very quickly. So what we do is we look and we say, oh my gosh, all these parts are kind of all connected to this top region of wire, okay? And all these parts are also connected to this bottom region of wire. And so what we end up doing is we say, okay, this bottom part we're going to just represent as with a symbol known as ground, and this top part we're going to represent just with the symbol of whatever the voltage is. And let's say this is a 3.3 volt source because we use that a lot. And what that ends up meaning is instead of drawing lots of circuits that look like this, we end up just using this a lot. So maybe 3.3 volts, a resistor, and then ground. And this is the same thing as the circuit we've been looking at a little bit ago, where this is a resistor.